Welcome, everyone, to the March 2024 Martin Gardner Celebration of Mind Talk. I'm your host, Bob Hearn, and we do this on the 21st of every month because Martin Gardner was born on October 21st. Today's speaker, I'm very pleased to be able to introduce Doris Schattschneider, who is incidentally the newest member of the Gathering for Gardner board. Doris is Professor Emerita of Mathematics at Moravian University in Pennsylvania. She is very well known for her work on tilings and also for her work on Escher. She has published a book about Escher and several articles and given many talks that many of you have probably seen. She's on the advisory committee of the National Museum of Mathematics, fellow of the AMS, and many other honors you can read in her bio on our Celebration of Mind webpage. So today she's going to be speaking to us about her work with Marjorie Rice and Pentagon tilings, which she's famous for and many of you are probably aware of, but it's going to be wonderful to hear it from her directly. So Doris, I will hand it over to you.
Thanks very much, Bob. And thank you everyone for coming. Some of you may have heard some of this before, but I hope that you'll enjoy it, even if you've already heard some of it. I want to speak about the work of Marjorie Rice, who is identified as an amateur mathematician merely because she had absolutely no formal training in mathematics. Marjorie was born in 1923 in St. Petersburg, Florida, and shortly after she was born, the family moved to Southern Oregon, a rural area where she lived on a farm and attended a one-room country school. She loved her teachers who encouraged her. She also loved arithmetic and mathematics and said she loved to figure out why things worked, why these algorithms that we would call them work the way they did. The family moved again to Florida, to Pine Castle, where she went to high school. And being a very practical sort, she chose to go the secretarial track. And in those days, the secretarial track didn't allow anyone to take more than a general math course. So that's the only mathematical training, if you wish, that she ever had. She married Gilbert Rice in 1945, and they settled in San Diego, California. He ran a printing business, and she was a full-time homemaker. She raised 5 children. And she was always interested in puzzles, in art, in logic games, and often when she traveled with her husband, she would tuck into her suitcase a puzzle book, as she said, to pass the time while they were waiting for various trains or buses or whatever. She also took out a subscription to Scientific American for her youngest son when he was in high school. And unbeknownst to the family, since she got the mail first, she was an avid reader of Martin Gardner's column in Scientific American. And in July 1975, her mathematical odyssey and connection with Gardner began. This was his column in the July 1975 Scientific American. It was titled "On Tessellating the Plane with Convex Polygon Tiles." And notice that he has an Escher tessellation included. And so for him, tessellations were a very interesting topic, not only of Escher's, but here he was going to be writing about tiling by convex polygons. And of course, he first began by saying that any triangle can tile the plane. You just take a triangle, rotate it about the midpoint of one side, you're going to get a parallelogram. And then, of course, you can just repeat those to fill the plane. Any quadrilateral will also tile the plane in the same manner. Rotate it 180 degrees about one edge, and then you get what's called a parhexagon with 3 pairs of parallel and equal sides, and that too will tile the plane. Even a non-convex quadrilateral will tile the plane in the same manner. And so triangles and quadrilaterals, any shape, will tile the plane. So that brings us to what other convex polygons tile the plane. And he next talked about hexagons and recorded that Karl Reinhardt in 1918 in his doctoral dissertation discovered 3 types of hexagons tile the plane, and also proved that these were the only ones. And what do we mean by a type? Well, these types or classes are defined by conditions on the sides of the polygon and the equations of angles. And where do the equations come from? Well, for the first one here that you see, type 1, you see it has 2 parallel and equal sides. So that would be a condition on the sides. But also, if you make the tiling with it, if you look at where where vertices of the polygon come together, that creates an equation. And in this case, it's angle A plus angle B plus angle C has to be 360 degrees. And there are other angle equations too, but this is the only one that is really needed to define this whole tiling. So each class is defined by a minimal set of conditions. That is, what sides are equal to each other. That means they're going to meet in the tiling and match up. And what are the angle equations? What angles have to come together in the tiling to add to 360 degrees? And so there are just these 3 types. We know that any regular hexagon will tile the plane. And these 3 types, the regular hexagon would fit into any of these 3 classes. It fits into all 3 because it certainly has 2 parallel and equal sides. And in fact, any 3 angles in it add to 360. So certainly A plus B plus C adds to 360. And you can look at the conditions on these 2 other types and see that a regular hexagon would satisfy all those conditions as well. So the next is convex pentagons. And although I note that no convex polygon with 7 or more sides can tile the plane, so in fact that leaves only convex pentagons. The fact that no convex polygon with 7 or more sides can tile the plane was kind of a folklore theorem when I was trying to write up this material originally. I couldn't find it written up anywhere. And so, in fact, Ivan Niven then wrote it up and had it published. Let's move on to pentagons. Reinhardt proved that there were 5 classes of pentagons, convex pentagons, that tile the plane. He never really claimed that there were only 5, but these 5 classes that you see all have a special property, and that is that if you take a single pentagon, then it can fill the whole plane just by using the symmetries or the motions that are in the symmetry group of the whole tessellations. So it only takes 1 tile to fill the whole plane if the symmetry group acts on it. And although Reinhardt never claimed that these were the only ones, evidently some other people, some other mathematicians got interested to see were there any more. And in 1968, Robert Kirshner published a paper in the Monthly that says here's 3 more that he had found, again, classified the minimal conditions on sides and angle equations. And so there's something different about these, though. These 3 classes, and here's you see the tessellations, a single pentagon in one of these classes can't fill the whole plane just by the symmetry group acting on it. You have to take it and its reflected image and make a pair, a joined pair like that. And then if the symmetry group acts on it, you can fill the whole plane. So these tilings are called two-block or two-isohedral or two-transitive tilings, whereas the ones that Reinhardt discovered are called isohedral or one-block transitive. So Kirschner, however, went further and claimed that now these 8 classes completed the problem. These were the only 8 classes of convex pentagons that can tile the plane. And then he followed with this remark: the proof that the list here is complete is extremely laborious and will be given elsewhere. Well, even though I can't hear you, I'm hoping you're chuckling at this, because this is reminiscent of Fermat's marginal note as to why a proof could not be given. And in fact, within just a month, someone, Richard James III in California, discovered another pentagon class that was not in this list of 8. In December 1975, Martin Gardner published this tessellation in his column as a follow-up. And this is quite different from any of the other 8. First of all, how did Richard James, discover this? Well, he began with the well-known tiling by octagons and squares, and noted that if you divide each octagon with a cross like this, then it divides into 5 congruent pentagons. And then you can pull those apart and fit in the empty space copies of those pentagons. And so here you have a tiling by pentagons. But if you look at these pentagons closely, you can see that, in fact, they have 2 parallel sides. And so that's just type 1. So although it was a new tessellation, it's not a new pentagon type. But if you skew the cross, as in the illustration in the Scientific American column, you do get a new pentagon type. And moreover, it takes 3 of these stuck together to create the whole tiling using the symmetries of the tiling. So this is a 3-block tiling, or a 3-isohedral tiling by pentagons. And also, it's not edge to edge. Some of the other pentagon tilings were also not edge to edge. And here are the general conditions on it. So this column that identified there was a new pentagon class just took Marjorie's fancy. She was so curious and thought that she would like to find some new ones. But maybe you're asking, how did you get interested in it? That is me. And it was because of what I call Martin Gardner's mathematical grapevine, or MG squared. Richard James made the discovery in July of 1975, very shortly after he read that column. He sent it to Martin Gardner, and Martin Gardner in turn sent it to Coxeter in Toronto. I happened to be visiting Coxeter that summer in August, and Coxeter showed it to me. And this was just one example. What James had sent to Martin Gardner was just one tiling, one example. And so on my way home on the plane, I played around with it and discovered, in fact, it was an infinite class, just as the other types were infinite classes. And so I sent my work to Martin Gardner. And Martin replied to me that he now knew I was interested in tiling and would be in touch if anything else came in. So Marjorie had set herself this problem: find other types of convex pentagons that can tile the plane, and also find some new tilings by convex pentagons. And this began a years-long odyssey. In 1976, Marjorie started work on this problem, and here's how she approached it. The first thing she did was draw up these little house-like pentagons, and then in symbolic notation was able to encode in these little symbolic pentagons the information for each type. For example, in this first picture, she's joined with this arch, angles A, B, and C. That's to indicate that A plus B plus C adds to 360. A plus B plus C come together in a tiling. And there's this straight line joining angles D and E that says those two add to 180, or they come together in a tiling. In the next one, she's doing a similar thing. She joins A and D and B. That's to say the sum of those three angles is 360, or they come together to make a vertex in the tiling. And similarly, C plus E is 180. They come together in a tiling, and so on. All these, what look like chicken scratchings, if you wish, in each pentagon record the angle relationships. And then she's also indicated on the sides of angles which sides equal each other. And those are kind of standard notation. So simply with this symbolic notation, she is able to record all the information for each class. By February 1976, she's discovered a new type and wrote to Martin, "Here, dear Mr. Gardner, here's a pentagonal tile that I believe is really different from any you had listed, though similar to type 7 and type 8. And the similarities were that there were 4 equal sides, and there were 2 equations of the form 2x plus y equals 360 degrees, and it involved all 4 of the 5 angles of the pentagons." And not only did she send these 2 different looking tessellations, they're just different shaped pentagons but the same combinatorial tiling, she also sent this picture of how the extremities of the infinite class of shapes that are in this particular class. And so Martin sent it to me and sent her work to me and asked, "Can you please verify if this is really true? Is this really a new type?" And I verified that it was and let him know that, although he never announced this in his column in Scientific American as a follow-up. I was intrigued by the conditions on this tiling that look so much like 2 of Kirshner's types as well, that I did what most mathematicians do. I made a conjecture, and I sent it to Marjorie Rice. And this is my conjecture: that any pentagon having 4 equal sides and containing 4 different angles, P, Q, R, and S, such that 2P plus Q is 360 and 2R plus S is 360, any pentagon that satisfies those conditions can tile the plane. And I just thought it might be interesting for Marjorie to look into that, and didn't expect to hear from her for quite a while. Well, in fact, about a week later, I get a reply: "The conjecture is false. There are exactly 4 distinct types of pentagons, as described in the conjecture, that do tile the plane, and 2 distinct types that do not tile the plane." And Marjorie's complete explanation was this: "This is the first time I'd seen any of her symbolic representations, and I, for the life of me, could not figure out what this was. There were no words, just pictures. And as I looked at it, I finally figured out what the chicken scratchings in those pentagons meant. That is, they were telling me the angle relationships. And then I had to figure out from the pictures why the circled ones could tile the plane and why the uncircled ones could not. It turns out that the first one circled was Kirshner's type 8. The last one, number 8, was Kirshner's type 7. The circled one, circled 5, was Marjorie's new type. And then number 6 circled was actually a special type 1. Notice that below it, she has written that A plus B is 180. That guarantees it's a type 1. And so why didn't the others tile the plane? Notice that the Y-shaped scratches in each pentagon tell me that twice this angle plus another angle equals 360. And twice this angle plus another angle equals 360. So these are all the combinatorial possibilities for the way that 4 different angles can be involved and creating these equations. So there are 8 types. And the ones that don't work, well, let's look at this one that is number 2. If you come down here, you can see from the equation that 2E plus B has to equal 360. So here she's got 3 little tiles and 2 angles E and angle B equal 360. But if that happens, then down here where she's shown with an arrow, 2 angle A's have to come together. But there's no equation in the minimal set of equations that says 2 angles A come together. And so that's why this can't tile the plane. And this similar argument over here for number 7. So what is all this stuff? Why can't 3 and 4 tile the plane? Well, what she's showing with a picture is that if you try to actually construct this, and evidently she did try to construct it, it ends up being degenerate. It's the only pentagon that will satisfy those conditions actually turns out to be a quadrilateral. In other words, one edge, it has 0 length. And so that was her complete solution to my conjecture. From March through November of 1976, Marjorie listed with her symbolic marked pentagon tiles. She made lists and examined and investigated, and she also called P1. She had new notation. P1 simply means pentagon for whose only involvement of angles in angle equations is each angle gets used exactly once. So type 1 and type 2 that were both in the original Reinhardt list just involve 2 equations and each angle gets used exactly once. P2 meant pentagons where each angle gets used exactly twice in the set of defining angle equations. And here was her list, again, of all the possibilities where that could happen. There were 12 different types in her list, 2 of which got eliminated as impossible, and then the others with her symbolic notation. And here's a picture of just some of her drawings that she would make of these various possible tilings. The shaded tiles are the reflections of the unshaded tiles. I've identified Marjorie's new discover in the lower left in one of these pictures. All the others are labeled not only with her label equations, but you can see from the tessellations which sides have to meet which sides. And each of these is also labeled with one of the listings in the previous list that I showed you. So she's keeping track of everything very carefully and identifying many, many new tilings. In August 1976, I was completing my draft of the article that I was writing for the Mathematics magazine. It was called Tiling the Plane with Congruent Pentagons. And I sent this off to Marjorie. And she noticed and corresponded back to me that it seemed to her like several of the tilings that the two block ones by Kirschner look like kind of double hexagons, stuck together hexagons. And she noted that she found these various ways at the top of the page of splitting a double hexagon into pentagons. Notice in most cases, the pentagons don't look congruent. At the top there they are, but the pentagons in the bottom row certainly don't look congruent. There were also 6 different ways that you could fit these double hexagons together. So this set her off on a whole new inventory of possible pentagon tilings, and also new ways to look at these double hexagon tilings, if you wish. And by December of that year, she discovered 2 new types of tiling pentagons. These would be called types 11 and 12. And notice that here, this definitely does look like a double hexagon. And down here, this looks like a double hexagon. So these were discovered using that idea of how can I tile with double hexagon types and split them into 4 congruent pentagons. She's now discovered 3 new types, and these are all infinite families. In 1977, I sent Marjorie the article by Grunbaum and Shepard, the 81 isohedral tilings of the plane. And notice that in these pictures, these are all combinatorially pentagons. That is, if you trace around a single tile, you'll see that there are exactly 5 vertices. And so what Marjorie did, and before I even mention that, notice that by looking at these shaped edges, these curved edges, you can easily see which edges match. For example, in this one, this edge surely rotates into this edge. And here we have an S-shaped edge, so that rotates around the midpoint at 180 degrees. And so on. You have these different edges. This edge will rotate around into this edge. So Grunbaum and Shepard made these shaped tiles with curved edges to make it easy for the viewer to understand which edges were related to which other edges. Strangely, what Marjorie did was make all the edges straight, turn them into convex pentagons, and then mark which edges match which edges by putting little marks on the edges. So she literally, although she didn't know it, reversed engineered what Grunbaum and Shepard had done, because in their original research, they had used tiles with straight edges and marked the edges with what they called adjacency relations. And so here Marjorie had actually reverse engineered for her own information what Grunbaum and Shepard had done to make it, quote, easier to understand. And she continued on. In the next year, she's extending her lists of 2-block pentagon tilings, searching through 56 different possibilities. and she sketched more than 100 different tilings. She was just indefatigable. By December 1977, she discovered a fourth new tiling pentagon, and this was called Type 13. Luckily, she sent it to me just in time to include in my article for Math Magazine. Marjorie was always interested in art as well. She took a correspondence course once in art, and of course, she was very aware of Escher's tilings and very interested in them. And so she used her pentagonal grids to create Escher-like tilings. Because of her discovery of these pentagon tilings and because of her studying them, she knew exactly for any pentagon tiling, exactly how the edges matched and exactly the shapes that would work. And so she was able to inscribe in a single pentagon a shape that overlapped the edges so that it would force the edges to match the pentagons around it. And here she's inscribed a single hibiscus. And from this, she created this beautiful hibiscus tiling. Here it is without the grid showing. In this particular tiling, the pentagon is displayed in 8 rotated positions. And so her coloring, which is quite beautiful, actually displays the 8 different colors of hibiscus to mark those positions. So each hibiscus in a particular rotated position is a single color. Here's a 3-block tiling by another equilateral type 2 pentagon, and here she filled it with shells. And here, a type 2 pentagon with 4 equal sides, she's filled with fish. And a type 13 pentagon, her last one, she's filled with butterflies. In 1993, I sent Marjorie, again, something that I thought she'd be interested in. This was combinatorial output from a computer program called Reptiles by Daniel Hewson. And it showed the combinatorial graphs of all possible edge-to-edge 2-block and 3-block tilings by pentagons. And there were 23 2-block tilings and 43 3-block tilings. So 66 tilings in all. And what Marjorie decided was she would study these tilings. Notice in this combinatorial output, none of these look like pentagons, but the combinatorial output was such that it would be easy to see. For example, in this one up here, this looks like 4 quadrilaterals, but if you look at and count the vertices, that is where 3 or more tiles meet, you can see that combinatorially they are pentagons. And there are 3 different shapes to easily see that these are 3 different classes of pentagons. We're going to look more carefully at the pentagon in number 56, right here. If you look carefully at this, you can see, again, here's a large patch of 3 stuck together, not looking like pentagons, but they are because there are 5 vertices. And so if you look right here, you can see that these repeat, and so this has to be a 60-degree angle. Similarly here, these repeat, and so this has to be a 120-degree angle. And so Marjorie decided not only to look through all of these, but she paid particular attention to this one. And so I want to go into some detail of what she did with this particular combinatorial tiling. She was able to discover that you can make all 3 pentagons congruent convex pentagons. Notice the difficulty of what she's doing. if you take a single pentagon, label it A, B, C, D, E, and then stick to it another copy of itself, there are 5 ways of sticking it face up, and there are 5 more ways of sticking it if you turn it over. These are in theory, of course. So there are 10 possibilities to check for each of the 23 2-block tilings. And if you go to 3-block tilings, you can stick another pentagon on those 2, and then that's 10 more possibilities. So there's 100 possibilities that have to be tested to see whether or not you can make a 3-block that will tile the plane. And so what did she do? She made a grid, a 10 by 10 grid that can test each of the 43 cases of 3-block tilings. So if we go back to this 3-block pentagonal tiling that we saw before, here is the 10 by 10 filled in by her, testing all of those cases. Now, where there's just emptiness, she could easily see that that was impossible. But for all the others that are filled in, she has actually gone through testing whether or not it's possible to have that combination of angles and sides make a tessellation. And you'll see that for almost all, except one, this one right here, that has a check mark, all are impossible, but here's one that looks like it will work. And so there's a close-up of that. And there again, she has her angle equations and the mark sides. We already saw that just by looking at the combinatorial output, one of the angles has to be 60 and one has to be 120. By looking at the angle equations, it's easy to figure out that another one has to be 120. And after working this out, in fact, she is then able to draw a picture of 3 congruent pentagons that satisfy all those conditions, and then work out the tiling based on those. She called this pentagon a versatile because actually it turns out that it can tile in many, many ways. It's not a new pentagon, although it's a little hard to see. It does, in fact, have 2 parallel sides because angle A plus angle E adds to 180 degrees. So it's a type 1 pentagon, but can make this very beautiful. This is her actual drawing, this very beautiful tessellation. And here is how you can generate this whole tiling. You take this block of 3, you rotate it about at 60-degree angle, and then you rotate it about the 120-degree angle, and then you get your whole tiling. You need actually 18 pentagons for a block that generates the tiling by translations. And in 1999, the MAA actually installed this tiling in the foyer of its headquarters, at my suggestion, of course. And they gave Marjorie the certificate of recognition when the tiling was installed. She also used this to create a beautiful tessellation of roses. One of the persons who was at one of my lectures and was so inspired by her work actually wrote a poem, and I want to just read it to you quickly. Her pentagons look like houses in the notations she devised, a modest mathematical suburb in California, a tessellated plane. In one house, the stick figure of a woman indicated the slide and rotation of the angles, as if she had inscribed herself into her work, made herself the symbol of a transformation. Because of the folding of sheets and the setting of tables, because of the daily reordering of the same small pieces of her life, because in the dailiness she discovered some idiomatic system of beauty. Her kitchen floor slowly puzzled itself into a Moorish garden, as an Escher of hibiscus protract into bloom. A quick finish. The state of the Pentagon tiling today is probably, as you know, complete. In 1985, Rolf Stein discovered type 14. This was unique. This was not an infinite class, unique up to similarity. So in a sense, just a single pentagon that can produce this tiling. And in 2015, Casey Mann, David Von Duro, and Jennifer McLeod Mann discovered type 15 with a lot of computer help. And it too was an outlier, a singleton, unique up to similarity. And in 2017, Michael Rao posted a proof there were no other tiling convex pentagons. I do not know if this has been formally published yet. It's been posted on the archive, and those who have looked at it seem to agree that the list of types is now complete at 15. Martin never published Marjorie's work, except in his follow-up book in 1987, Time Travel and Mathematical Bewilderments, that reproduced the original column with comments and updates. And he included Marjorie's discoveries and spoke of her fantastic achievements. So Marjorie Rice, with not even a high school geometry course, working completely with pencil and paper, found 4 new types of convex pentagons, more than any trained mathematician since Reinhardt. She found all 22 edge-to-edge 2 isohedral pentagon tilings that were verified by Houston's computer program. She found more than 45 possible edge-to-edge 3 isohedral pentagon tilings. In all, she discovered and drew by hand hundreds of tilings by convex pentagons. And using pentagonal tilings as grids, she produced several Escher-like tilings by flowers, shells, fish, and other motifs. She studied Grunbaum and Shepard's book, Tilings and Patterns, and studied and analyzed aperiodic tilings, something I couldn't get into today, as well as producing new spiral tilings by non-convex pentagons. Again, something that's a whole other talk. And Marjorie died in 2017, and her research materials, her original sketches, and her Escher-like tessellations, and 30 years of correspondence with me now reside in the University of Calgary Library as part of the Eugene Stren's Recreational Mathematics collection. Her family donated all that in 2018, and this past fall, I took my whole file of correspondence with Marjorie and included many, many of her sketches to complete that collection. So all of it is now at the University of Calgary. And these are the various publications of Marjorie's work that you might be interested in. I'll leave that up for a couple of minutes or a couple of seconds, really, if you want to take a picture, because I want to announce that next year there'll be a wonderful new book about Marjorie's work, but it's a children's book, The 5 Sides of Marjorie Rice, How to Discover a Shape. This is a very charming book that's been written by Amy Altsnauer and illustrated by Anna Braun. And I hope you'll look for it. It'll be a wonderful gift for children and for yourself about Marjorie and her life and her tessellations of pentagons. So that's it for now.
Thank you, Doris. That was delightful. And I'm very excited to hear about the new book. I was not aware of that. We do have a little bit of time left. I did see one question during the talk. Did she use watercolors to produce her art? Do you know?
I believe it was pastel pencils.
Mm-hmm.
It was not watercolor. They were usually done on kind of a vellum or a strong type of tissue paper. And I think that was so that, you could see through it. Um, but they're quite beautiful.
Yes, they really are. Yeah, I've heard this story a number of times, but I never tire of hearing it again. So thank you very, very much for that. I mean, I have to say, I spent when the 15th tiling was discovered, I spent a lot of those 2 years myself trying to prove that the set of 15 was complete. But Raoul beat me to it. But it was a lot of fun trying to work in that space.
Do you know if there is a formal publication of Rao's proof and verification? I know
Not that I'm aware of. Craig, should know better than I, says I don't think so.
I didn't think so either. So it still hasn't been formally uh, vetted or
Yeah, it's kind of a tricky paper to read, but everybody who has thoroughly studied it seems convinced. I was convinced.
Mhm.
Did Marjorie's work on aperiodic tiles relate to Roger Penrose's work?
It related more to Amon's work. There's in the Grunbaum and Shepherd book, he does spend some time speaking about the work of Robert Amon. And Marjorie's annotated version of that book, which is now in the University of Calgary, shows that she really studied that pretty hard. So I think she was more interested in trying to find a new aperiodic tiling.
Hmm.
And in fact, she did make some sketches, and at one point she thought she had an aperiodic tiling, and then she herself disproved it. But she really studied the Amon work.
Do you think that Marjorie's work was sent to you entirely because your research was in this area, or also because you were both female and perhaps you might have been more likely to take her work seriously?
I don't know if it had anything to do with my being female. I think that once the contact was established, because Martin sent her first discovery to me to be vetted and verified, uh, we struck up a correspondence. She did end up corresponding with some other people, and I was surprised to discover that she I suppose people wrote to her and then she struck up a correspondence with them. As far as I know, she didn't correspond with anybody else specifically about discovering new pentagons, but other people who had discovered, for example, there was a gentleman in Australia who hooked rugs
Hmm.
in Pentagon tilings. And there was Michael Hirschhorn in New South Wales corresponded with her because he did some workshops with students on discovering tilings by equilateral pentagons. And so he probably wrote to her and they struck up a correspondence. So she did correspond with other people, but I didn't I wasn't aware of any that she corresponded with specifically about discovering new types. I did meet her several times, by the way, and visited her. Um, very happily, the joint mathematics meetings are in San Diego every 5 years. So anytime I was in San Diego for the math meetings, I would always visit with Marjorie. And at some point after the Geometer Sketchpad was created and published, I presented her with a copy of that. So in her later years, she was actually learning to use a computer and was able to do some drawings with Sketchpad. But all of her research was by hand.
Thank you. A few more questions in quick reverse order. What did Marjorie's family think of her work in this area?
Well, I think at first she kept everything from them. She would hide her work in a kitchen drawer. None of them knew what was going on. So she did this in secret. Um, But once it was discovered, I think her husband was perplexed by it. When I visited her and met him for the first time, he asked me if she could make any money from it. I had to laugh because I said, well, the tessellations maybe, but I don't think you're going to make money from discovering new Pentagon tiles.
Not
And
not one of the millennium problems, alas. Yeah.
right. But uh, as once they knew it, I think they were very proud of her work. I think they were a bit perplexed by it too, and I don't think her one daughter, I think, was very pleased with the artistic part and actually put up a website for her showing her tessellations. But she kept it secret for quite a while.
Wow. Do you know whether she lived to see Rao's proof that there were only 15?
No, she didn't. She died in 2017,
Mhm.
and I guess that's the same year it was. No,
Yeah.
that was the same year. No, and she did suffer dementia the last few
Mhm.
years of her life. The last time I visited her was rather she kept a lovely personality, but she looked at her work and she said, "Did I really do that?" And even she was mystified by her own work,
Yeah.
which is sad.
Yeah. Um, can you show your slide again, listing her discoveries and investigations?
Sure.
And while this is up for people to read, let's see. What aspects of her mathematical reasoning do you find most surprising or remarkable?
I think the notation
Mhm.
was an incredible breakthrough because if you know anything about combinatorics, as soon as you label A, B, C, D, E for the vertices of a pentagon, you've got to worry about, if you prove something with labeled in one way, then you've got to worry about cyclic um, transformation, permutation, and then even turning it over.
Mhm.
With that symbolic notation, you don't have to worry about any of that. So it's an incredible breakthrough in terms of being able to very quickly record information and show information.
It's a little bit reminiscent of Feynman diagrams or something like that. It's amazing how a new notation can suddenly really illuminate a problem.
Right.
Let's see. Did her son read about her in Scientific American? Do you know?
Well, she was never published in Scientific American.
Right, right. Okay. Yeah, you mentioned that.
Uh, it wasn't until Martin Gardner's book, the follow-up book, which was 1987.
Yeah,
And I'm sure that they would have read about it then, but that was long after the
right.
discovery.
Thank
Leave.
you. Thank you again very much, Doris. That was wonderful, and we appreciate you stepping up.